Today we will start the fourth lecture of this course, Artificial Intelligence. Today's topic is uninformed search. In the last class we saw how the state space can be represented. Today we will look at some of the strategies and algorithms that are used for search. Before we start today's lecture, we will look at the questions of the previous class and the answers to those questions. The first question of the last class was this: consider the following as a state space search problem. Choose a formulation that is precise enough to be implemented. For each of the problems that we have described, you would have to show the representation of the state, describe the initial state and the goal test, and describe the successor function. The problems that we looked at in the last class were: number 1 was the graph coloring problem. In the graph coloring problem, you have to color a planar map. So, you have a map which has a number of regions. So, all of you are familiar with maps, and then you know in the map there are several regions. These regions may denote different countries and or different states, and you have to use some number of colors to color these regions such that no two adjacent regions has the same color. Now, we will look at our representation of this map coloring problem. Rather than graph coloring, this is the map coloring problem. So, what we will do is we will first represent the map by a graph. For each region we will have the vertex of a map. Suppose this is region A, this is B, this is C, this is D, this is E, and this is F. So, we will say that the region A corresponds to the vertex of a graph. B and F are adjacent to A. For B, A, F, and then D and E, these are adjacent to B, and so on. So, we will represent this map by a graph, where for every region we will have a vertex of a graph, and if two regions are adjacent, we will have an edge connecting those two vertices. So, we will call these vertices as V1, V2, Vn, and we will represent the colors by C1, C2, C3, C4. In the map coloring problem, we will use 4 colors to color the map. In fact, it has been shown that any planar map can be colored by 4 colors. We will not talk about the proof in this class, and it is not within the scope of this course. So, what we will do is a state will be represented by a n tuple. So, for every region we will have one entry in the state representation. If a region is colored by a particular color, we will use that color as the attribute for that region. If a particular region is not colored at a particular time, we will represent that region by X. So, let us look at this example. So, this is an example of a map. In this map, there are 5 regions A, B, C, D, and E. Corresponding to this, we are constructing a graph which has 5 vertices. Now, A and B are connected, A and D are connected, B and C, B and D, C and D, C and E, and D and E. So, this graph represents this map. Now, this is a particular state of the graph where A and E are colored blue, B is colored green, C and D have not been assigned colors as yet. We will represent this state as blue, green, X, X, blue. So, for this map coloring problem, in the initial state we will start with all the states unassigned, all the regions unassigned, none of them has been assigned a color. And we will have reached a goal test if when all the 5 regions are colored such that if 2 vertices Si and Sj are adjacent, their colors are not equal. So, a goal state is a state where all regions have been assigned colors and the coloring does not violate the constraints. Now, what are the different operations that we can apply to the state space? For example, this is a particular map. We can apply the following operator: change to yellow, that is change region 2, that is B, to the color yellow, and as a result we get this state. Now, on this state, if I again apply the operator change 3 green, we get this state. So, this is the state space representation of the graph coloring problem. The second problem that we assigned in the last class was the travelling salesperson problem. In the travelling salesperson problem, we have a map involving n cities, some of which are connected by roads. The objective is to find the shortest tour that starts from a city, visits all the cities exactly once and comes back to the starting city. Now, this is how we will represent the travelling salesperson problem. This is the map, this is the graph corresponding to the travelling salesperson problem. A, B, C, D, E are the different cities. There are roads connecting some of these cities. For example, the distance between city A and B by the direct road is 94 units. Distance between A and D is 384 units. Distance between A and E is 190 units, and so on. So, we represent by Y the set of cities. So, in this case, Y equal to the 5 cities A, B, C, D and E. We represent by this distance function dxy the distance between cities x and y. Now, corresponding to this travelling salesperson problem, we will design the state space. In the state space, a state would be represented as a path connecting a number of cities, such that in this path no city is visited more than once. So, such a path is called a Hamiltonian path. In graph theory, such a path is called a Hamiltonian path. So, a state for our state space representation will be a Hamiltonian path in this graph. A Hamiltonian path is a path which does not visit any city twice. Now, for our representation, x will be the set of states in our state space representation. Each state is a Hamiltonian path of this TSP graph. So, each state is represented by x1, x2, x small n. This is a path such that each of these xi corresponds to a city and no two cities are same, that is xi not equal to xj unless we get the full travelling salesperson tour, that is I equal to 1 and j equal to capital N plus 1, where there are n cities in this TSP problem. So, we have n cities. A TSP tour is actually a tour of n plus 1 cities, where the first city is the same as the n plus 1th city. So, the salesperson completes a tour of all the cities and comes back to the starting city. Every other city in the path is distinct. So, this is the representation of a state. The successor of a state x1, x2, xn is represented like this. So, delta x1, x2, xn the successors of this state are all states which are extensions of this Hamiltonian path. So, are those states which are x1, x2, xn, xn plus 1, where xn plus 1 is a city which is not equal to any other city which already existed in this path. Now, this is the state space representation of the TSP problem. What is the goal? The goal, a goal state is a state where we have a Hamiltonian tour of length n plus 1. So, the set of goal states include all states of length n plus 1. The third problem that I said you in the last class was the missionaries and cannibals problem. 3 missionaries and 3 cannibals are on one side of the river. There is one boat which can carry only 2 persons at a time. Missionaries must never be outnumbered by cannibals. You need to give a plan to cross the river, and for this problem I wanted you to come up with the state space representation. Now, the answer to this is, one way of representing a state is by a 3 tuple, where we represent MCB. M is the number of missionaries on the left bank. So, this is a river which the missionaries is trying to cross. Initially, we have 3 missionaries and 3 cannibals on the left side of the river. So, this is the left side and this is the right side, and we have one boat, and this boat is initially on the left side and can carry 2 people. Now, the state will be represented by 3 numbers. M is the number of missionaries on the left bank. So, initially M is 3. In the goal state, M will be 0 because all the missionaries need to be on the right bank. C is the number of cannibals on the left bank. Initially C is 3. In the goal state, C will be 0. And B is the position of the boat, whether the boat is on the left bank or the right bank. In the beginning, the boat will be on the left bank. So, the initial state will be represented by 3-3L, that is 3 missionary, 3 cannibal on the left bank and the boat also on the left bank. And the goal state will be represented by 0-0R, that is no missionary on the left bank, no cannibal on the left bank, 3 missionaries on the right bank, 3 cannibals on the right bank, and the boat is on the right bank. The operators for this problem is a 2 tuple M and C. So, M is the number of missionaries on the boat, C is the number of cannibals on the boat. Since only at most 2 persons can be in the boat on the same time, the possible operators are 10, 20, 11, 01 and 02. And 00 is not a valid operator because the boat needs at least 1 person to steer the boat. Now, so what we find is that each state is represented by a 3 tuple M, C, B. So, M can take 4 values 0, 1, 2, 3, C can also take 4 values 0, 1, 2, 3 and B can take 2 values L or R. Therefore, the possible number of states are 4 into 4 into 2, that is 16 into 2, 32. These 16 contains the boat on the left side, this 16 contains the boat on the right side. But some of these states violate the constraints that missionaries must never be outnumbered by cannibals on any side, because otherwise the cannibals will devour the missionaries. And if we apply that constraint, these green states become invalid states. So, finally, we have these are the only valid states. So, there are 20 valid states in this state space, and if we apply the operators to each of this state, we get the state space graph. This is the initial state, 3-3L, 0-0R is the goal state, and these arcs denote the successors of each state, the operators that can be applied on each state to go to the other state. So, this is a state space representation of the missionaries and cannibals problem. Now we are ready to start today's lecture, which is of module 2, which I started in the last class, problem solving using search. In today's lecture we will talk about uninformed search. The instructional objectives of today's lecture. In this lecture, the student will learn the following strategies of uninformed search: breadth first search, depth first search, iterative deepening search, bidirectional search. So we will look at these 4 strategies for uninformed search. We will know what uninformed search is. Uninformed search means searching through the state space without using any extra information, without using any domain specific information. For each of these search strategies, the student will learn the algorithm for this strategy, and we will analyze each of these algorithms to find their time and space complexities, and the student will also learn when to select a particular strategy for a given problem. On what basis, given a problem, which strategy is the best strategy to select. At the end of this lesson, the student should be able to do the following. He should be able to analyze a given problem and identify the most suitable search strategy for the problem. Given a problem, she should be able to apply one of the strategies and find the solution to the problem. Find the sequence of nodes that will be expanded and what would be the final solution that will be obtained. So let's go back to a quick recapitulation of the search problem, of the representation of the search problem. So we have seen in the search problem, we represent S to be the set of states. The initial state is small s 0, which is a member of capital S. We have a set of operators or actions A, and we have a set of goals G, represented by an explicit set of goal states or represented by a goal test or by explicit goal states. A solution to a search problem is a plan which is a sequence of actions A0, A1, An, which leads to traversing a number of states. Starting from state S0 by applying action A sub 0, the agent goes to state S sub 1. From S sub 1 by applying action A sub 1, the agent goes to S sub 2 and so on. Finally, the agent arrives at state Sn plus 1, and if this plan is a solution to the search problem, then Sn plus 1 must be a goal state. And we also mentioned that for every path we will associate a cost. So path cost is a positive number. Usually path cost is the sum of the operator costs. Now this is the state space of the missionaries and cannibal problem, which we just discussed. Now let us see what is a plan for this missionary and cannibal problem. So we have already seen what is the state space for this problem, and we have identified that 33L is the initial state and 00R is the goal state. Now let's quickly look through the problem, look at the graph and trace a solution. So 33L is the initial state. We will trace a solution. So one of the operators brings which operator? By taking 2 cannibals by a boat, one comes to the 31R state. From there the agent can come to the 32L state and then to the 30R, 31L, 11R, 22L, 02R, 03L, 01R, 02L and then 00R. So this is a solution to the missionaries and cannibal problem. By applying a sequence of operators, the agent can traverse the state space and reach the solution. Now, in today's lecture, we will look at various strategies to systematically explore the state space by using a search graph or a search tree. So, corresponding to this state space, we will see how to construct the search tree or a search graph. And we will also see how to systematically explore this search tree or search graph in order to find a plan or a solution to this problem. Now, this is an abstract example of a very simple state space. We have these 8 states A, B, C, D, E, F, G, H, and these arcs show the connectivity information between the states. A is the initial state and G is the goal state. Now, when we look at a search algorithm, we would be interested in finding a path from the start state to one of the goal states. Now, there are several alternatives for which our algorithm will strive for. The objective of the algorithm may be to find the shortest path from the start to a goal state, or it could be to find any path from the start to the goal. Today, we will look at blind search or uninformed search, which I mentioned means that the algorithm does not use any information about the domain. And the most important blind search strategies are breadth first search and depth first search, in short BFS, or breadth first search and depth first search. Now, we will see what is a search tree corresponding to a problem and how do we get the search tree. This is the state space graph. From this state space graph, we will start from the initial node and we will list all possible paths. So, we start from A. From A, one can go to B or C. From B, one can go to D or E. From D, one can go to C or F. From C, one can go to G. From F, one can go from G to H. But from G, one can go to C or F. From G, one can go to C or F, etc. So, actually, if we take this graph and unfold this graph into a search tree, we may get an infinite search tree. In order to make this search tree finite, we will need to eliminate cycles from every path. That is, if in this path we have already visited C, therefore, from G we will not come back to C. Anyway, G is a goal state. So, in order to construct a search tree, we start from the initial state, we unfold the graph and we list all possible paths until one reaches to a goal state or to a dead end, and the result is a search tree. Now, let us look at some terminologies corresponding to a search tree. Now, the root node is the node from where we initiate the search tree. So, in this example, A is the root node. The leaf nodes are the leaves of this tree. This particular tree has the following leaves: G, G, H, E, E, G, H, G, out of which G is a leaf node because G is a goal node, and E and H are leaf nodes because we have reached dead ends. For the search tree, E's ancestor is B, E's parent is B, and ancestors are B and A. For this node F, the ancestors are D, B, and A. The descendants of F are G and H. Descendants of C are D, G, B, F, E, G, and H. branching factor means the maximum number of children of a node. So, in this particular search tree, we see that every node has less than equal to 2 children. Therefore, in this case, branching factor equal to 2. We represent the branching factor usually by this notation B. ABDCG is a complete path. ABD is a partial path. So, more terminology we will discuss as we come across them. Now, let us look at a basic search algorithm, a basic way of systematically searching the entire search space, and we will put certain restrictions on this general search algorithm to come up with special algorithms. So, in the basic search algorithm, we maintain a data structure called the fringe. So, fringe is referred by many people as open or queue or frontier. Okay. So, fringe will contain those nodes that our algorithm can expand at a particular time. Initially, fringe will contain only the initial state of the state space. Fringe is a list which contains the initial state in the beginning. The search algorithm will execute this loop. First step, if fringe is empty, if there is no more state to expand and the algorithm has not found a solution yet, the algorithm returns failure. If fringe is empty, return failure, that is no goal found and no node remains to be expanded. Otherwise, the algorithm removes the first node from the fringe. The algorithm removes the first node from the fringe, and let us call this node. If node is a goal, here the goal test is applied. If node is a goal, then the algorithm returns the path from initial state to node. Starting from initial state, when the algorithm expands node, finds that node is a goal, the algorithm needs to return the path to come from the initial state to the goal. Otherwise, it will generate all successors of node and incorporate those successors of node into fringe. The algorithm will put the newly generated successors into fringe. How these new nodes will be placed in fringe will depend on a particular algorithm. So, this is the basic search algorithm. You start from the initial state and then you expand its successors so that you can get new nodes. When you select a node for expansion, check if it is a goal. If it is not a goal, you expand it and get its successors. The successors are put into fringe, which are potential nodes. Now, we will discuss several search algorithms today. For each of these algorithms, we will look at the following. We will like to measure how effective these algorithms are in terms of completeness. Number one, completeness. Is this algorithm guaranteed to find a solution if a solution exists? Given a problem, given the state space representation of the problem, if a solution exists to this problem, can the algorithm find the solution, or is the algorithm guaranteed to find the solution? Secondly, we will evaluate whether the algorithm always results in an optimum solution. If a solution is found by this algorithm, is the solution guaranteed to be the one that has minimum cost? Thirdly, we will look at the efficiency of the algorithm. Namely, we will look at the time complexity of the algorithm, which is the time taken measured by the number of nodes expanded, either in the worst case or average case, to find a solution. So, we will look at the time complexity of the algorithm. We will also look at the space complexity of the algorithm, that is the memory required by the algorithm, which we will measure in terms of the maximum size of fringe. Fringe is the list the algorithm must keep track of. How big can be the size of fringe in the worst case or average case? That would be a measure of the efficiency of this algorithm, or whether the algorithm is practical at all. As I mentioned, today we will look at several blind search strategies: depth first search, breadth first search, iterative deepening search, and bidirectional search. In the subsequent classes, we will look at informed search, search using a heuristic function, and we will also look at constraint satisfaction problems, which can be modeled as search problems, and two-person games or adversarial search. Now, the first algorithm that we will discuss is breadth first search. We will see how the basic search algorithm can be modified to give rise to the breadth first search algorithm. So, this is the search algorithm that we discussed, and we mentioned that in order to have different strategies, we need to change the way this step works. Merge the newly generated nodes into fringe. How should we merge the newly generated successors into fringe? That will determine what sort of search strategies we get. So, the strategy in breadth first search is to expand the shallowest node first. In order to achieve this, the merging of successors into fringe will take place like this. We will add the generated nodes to the back of fringe. Fringe is a list of nodes which are waiting to be expanded. The new nodes which are generated will be put at the back of fringe, and we will see that this strategy results in the expansion of the shallowest nodes earlier than the deeper node. So, suppose this is a search space, a very simple search space. We will see how we apply breadth first search on this search space. Now, we have seen earlier that this search space gives rise to this search tree, and breadth first search will actually search on this tree in order to find a goal. Now, this is the potential search tree that can be generated by search. Initially, we have in fringe a single node A. So, this node is the only node in fringe. Now, we will execute the loop of our algorithm, which says that remove. This says that remove the first node from fringe. The first node is A. So, we will remove this node from fringe and get its successors. The successors happen to be B and C. So, A will be removed from fringe and B and C will be incorporated at the back of fringe. There is nothing in fringe, so B and C will be put at the fringe. Okay. So, what should be the next step? B has to be removed from fringe, as B is the first node in fringe, and its successors D and E will be generated. So, B has to be removed from fringe and its successors D and E are generated. At the next state, C is removed from fringe and its successors D and G are generated and put at the back of fringe. Next step, D will be selected for expansion. So, D will be removed from fringe and its successors C and F will be generated and put at the back of fringe. Next step, E has to be removed from fringe and its successors have to be put at the back of fringe. E has no successors, so E is simply removed from fringe. So, you notice here that this is the order in which nodes are expanded. First A is expanded, then B, then C, then D, then D, then E, then F, then G, etc. So, in breadth first search, nodes are expanded in this order according to their level. First A, then B, then C, then D, E, D, G. So, nodes will be expanded in the order of their depths. Okay, so let us continue. E has been removed from fringe, and then D will be removed from fringe and its successors B and F will be added to the back of fringe, and then G is the next node to be expanded and G happens to be a goal node. So, in this case search will stop. So, we notice that first all nodes at level 0 from the start state, depth 0 from start state they expanded, that is A itself. Then all nodes which are at distance 1 from the start state, then all nodes at distance 2, then all nodes at distance 3 and so on. Now, we will analyze this algorithm and look at its properties, whether breadth first search is optimal, whether it is complete, and we will also look at the time and space complexities. So that we can discuss about the time and space complexities of this algorithm, we must assume a particular structure of the state space. So, what we will do is, we will assume that in our state space, we have a very uniform type of search tree. Having a uniform search tree will enable us to analyze the complexity. So, let us assume that every node has at most B children, or let us say exactly B children. So, every node has exactly B children, and let us assume that D is the depth of the shallowest goal node. So, there can be many goal nodes. Let us say that the shallowest goal node is at depth D, and let M be the depth of this entire search tree. So, M is the maximum depth. So, let us just, M is the maximum depth of the search tree. So, D is the depth of the shallowest goal node, M is the maximum depth of the search tree, and we have a uniform search tree where each node has exactly B children except the leaf nodes. So, under this assumption, let us look at the properties of breadth first node. We have seen that the breadth first node, the generated nodes are put at the back of fringe, that is, new nodes are put on the fringe in first in first out order or FIFO order, okay, like a queue. So, fringe is actually implemented as a queue, new nodes are put at the back of the queue, and the node to be expanded is the first node in front of the queue. Firstly, breadth first search is complete, that is, if a solution exists, breadth first search which systematically expands 0 level nodes first, then all 1 level node, then all 2 level nodes, all 3 level nodes, will eventually expand all D level nodes, and it will come to the goal node which is at level D. So, breadth first search is a complete search algorithm. Secondly, breadth first search is optimal if all operators have same cost. You notice that breadth first search expands node according to their level. So, a node at level D will be expanded before any node at a larger level is expanded. So, breadth first search will expand that goal node first, which is at the lowest level. So, if our search cost is equal to the number of steps to the solution, breadth first search is optimum. However, if operators have different costs, then a goal node at depth 5 may have a cost of 10, whereas a goal node at depth 3 may have a cost of 23. So, in this case, breadth first search may not be optimum. So, breadth first search is optimum if all operators have same cost. Otherwise, breadth first search finds that solution whose path length is shortest, but path cost it is not necessarily the cheapest. And finally, about the time and space complexity. So, if we go back to the previous slide, you see, suppose this is the search tree and this is depth D and there is a goal here at depth D, G1 is at depth D. Breadth first search will expand all these nodes, all the nodes up to depth D minus 1 and some of the nodes at depth D in order to get this solution. Therefore, the number of nodes expanded by breadth first search is equal to order of b to the power d. And the number of nodes which are at fringe is also of the order of the maximum number of nodes at a depth. So, we can see that the time and space complexities of breadth first search are both of the order of b to the power d, where d is the depth of the solution and b is the branching factor at each node. Okay, wait. Now, so in breadth first search, if we have a complete search tree of depth d where each non-leaf node has b children, then breadth first search will have a total of 1 plus b square plus b to the power d, that is b. So, this is b to the power d plus 1 minus 1 divided by b minus 1, which is order b to the power d nodes will be expanded by breadth first search. For example, if we have a complete search tree whose depth is 12 and every node up to depth 11 has 10 children, then the number of nodes expanded by breadth first search will be order of 10 to the power 12, that is 10 followed by 12 zeros. To give you an idea of how big this number is, if we have a computer where 1000 nodes can be expanded per second and each node uses 100 bytes of storage, then breadth first search will take 35 years to run in the worst case and it will use 111 terabytes of memory. It's a truly frightening figure. So, the time and space complexities of breadth first search are exponential in terms of d, that is the depth of the solution. The advantage of breadth first search is that it finds a path of minimal length to the goal, but one of the major disadvantages of breadth first search when we compare it to the next strategy, depth first search, is that breadth first search requires the generation and storage of a tree whose size is exponential. So, it requires exponential space to store the fringe and it also requires exponential time. In the next class, we will look at uniform cost search, which is optimal in terms of giving the lowest cost solution. But today let us look at the other search strategies. Now we come to the next search strategy, which is depth first search. Depth first search, this algorithm will be again a variation of the basic search strategy that we outlined in the beginning, where instead of merging the newly generated nodes into fringe, we will give a particular strategy for merging. In breadth first search, we put the generated nodes at the back of fringe. In depth first search, our objective is to expand the deepest node first, and to achieve this we add the generated nodes to the front of fringe. That is, fringe is maintained as a last in first out structure or a stack structure. Newly generated nodes are put at the front of fringe. Now let us use the same search tree that we analyzed earlier and trace depth first search through this search tree. Now initially the fringe will contain the node A. Next step, A will be removed from fringe and its successors B and C will be generated and put in the beginning of fringe. Now B will be removed from fringe and its successors D and E will be put in the beginning of fringe. Next, D will be removed from fringe and its successors C and F are generated and put in the front of fringe. Next, C is removed from fringe and its successor G is put at the front of fringe. At the next level, G will be expanded, found to be a goal node. So we terminate our search after having found this goal node. So we notice that A, B, D, C and G are the nodes expanded. A goal node at depth 4 has been found by depth first search. On the same search tree, we saw that this goal was found as a result of breadth first search. This goal is at depth 2, and in that case we had expanded A, B, C, D, E and D. So let us analyze the characteristics of depth first search. In depth first search, we enqueue the nodes on fringe in a last in first out order by using a stack. Depth first search also requires exponential time, order b to the power d, to explore the entire search space. However, if you notice, the size of the fringe is at most the maximum depth of the tree. So the space required is actually order Bm, where m is the depth of the entire search tree, and the time required is order b to the power d. Depth first search may not terminate if the search tree is infinite. If the search tree is infinite, depth first search may not terminate. However, if it does terminate, the time taken is equal to the size of the search tree, if the search tree is finite at the worst case, and the space taken is order of depth of the search tree. So one advantage of depth first search is that it only takes linear space. However, the other characteristics are not that good, in the sense that it is not complete. It may not be able to find the solution if the search tree is infinite, and when it does find a solution, the solution may not be an optimum solution. Now, to recapitulate, let us look at the state space search problems. A state space is a graph VE, where V is a set of nodes, E is a set of arcs. Each arc has a cost. And in order to run these data structures, we will use run these algorithms, we will use the data structure for every node. this is very important. Every node data structure will contain the description of the state, the parent of the node. We see that keeping information about the parent is very important if we have to retrace the solution. So, when we get a goal node, in many cases we need to output the solution by which this state was obtained. So, to find the solution, we need to keep track of the parent of each node. For some algorithms, we may need to keep track of the depth of the node. We also need to keep track of the generator, the operator that generated this node. The last, if you want to find the output, the final plan, we need to find the operator that generated this node, and we need in some case to keep track of the cost of the path, especially when we look at uniform cost search and best first search. In subsequent lectures, cost is important, but at least we need to keep track of the state description, the parent and the operator, and some algorithms we need to keep track of the depth and sometimes the cost. A solution we have seen is a sequence of operators associated with a path from a start node to a goal node. Now, for large state spaces, it is not practical to represent the entire space, right. So, the state space, like for example, the 15 puzzle problem, we may not generate the entire state space and represent it as an explicit graph. Rather, we will, as we expand and generate nodes, we will make explicit only a portion of the implicit state space graph that is required for us to obtain a solution. We need not unfold the state space all at a time. So, we can work with implicit state spaces and only make those portions explicit by our successor generator operations. Now, each node, because at every node we keep a link to the parent of the node and the operator that generated the node, every node represents a partial solution path from the start to the given node. And from this node we can expand this partial solution to get maybe one or more actual solutions. Our search process will construct a search tree where the root is the initial state and the leaf nodes are those nodes. For this search tree that we currently have, the leaf nodes are the nodes which we keep at fringe. They are those nodes which are not yet expanded, that is, which have been generated, they are yet to be expanded, or those nodes that have no successors, that is, they are dead ends. The search tree may become infinite even when the search space is finite, because there could be loops in the state space. And in some cases, our search algorithm needs to return the entire path, in some cases only the final state. For example, in the 8 queens problem, the final state is just the placement of the queens on the board. We need not give the solution path, because given the state, the solution path is evident. For the 8 puzzle problem, the final state description does not carry any information as to how that state was reached. So, we have to output the entire solution plan. We mentioned that depth first search may not work in infinite state spaces where it may not reach a solution and go into an infinite loop. So, we have a variation of depth first search which we call depth limited search, where we cut off search at a particular depth. So, depth limited search works like this. At every node we keep track of the depth or level of that node, and we modify depth first search so that if depth of node which we are trying to expand is equal to limit, then we terminate the search. So, if we modify depth first search by cutting of search at a limit, we get depth limited search, which takes as parameter a depth limit and does depth first search up to that limit. Now, if we choose a limit beforehand, a solution may not be found at that depth, and therefore we have a variation of depth first search which is called depth first iterative deepening search. The idea is that we do DFS up to a limit. If we do not find a solution, we increase the limit by 1 and continue. So, until solution found, do DFS with depth cut of C, then we put C equal to C plus 1 and so on. So, depth first iterative deepening is a complete search strategy where initially we set limit to 1, then to 2, then to 3, then to 4 and so on. The advantage of iterative deepening search is that it has linear memory requirement, because at every step we do a depth first search, and we start with limit equal to 1, then to limit equal to 2, then limit equal to 3, and therefore it is guaranteed that when the algorithm finds a goal node, it is a node of minimum depth. So, let us illustrate this. So, this is a search tree. If we do iterative deepening search, this is the first node to be expanded. So, initially limit is equal to 1. So, we get this node, then this node, then this node. For the second depth limit with limit equal to 2, this node is expanded, then this, then this, then this, then this, then this, then this. Then we set limit equal to 3, for which we get this, 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 this and so on, and then we set limit equal to 4, and we have a depth first search of the search tree with depth bound equal to 4. So, depth first iterative deepening is complete. It is optimum if all operators have the same cost, and its time complexity is a little worse than breadth first search, because you notice that some nodes are expanded more than once, they are repeated. However, the order of node expansions is almost similar to breadth first search. So, if branching factor is B and the solution is at depth D, then nodes at depth D are generated once, nodes at depth D minus 1 are generated twice and so on. And therefore, if we this is the number of nodes, total nodes expanded by depth first iterative deepening, which is actually of the order of B to the power D. However, depth first iterative deepening search has linear space complexity unlike BFS, and it is complete, and it is usually the preferred algorithm for large state spaces. I come to the questions for today's lecture. Question 1, you are given a 5-gallon jug and a 2-gallon jug. Initially the 5-gallon jug is full and the 2-gallon jug is empty. Your goal is to fill the 2-gallon jug with exactly 1 gallon of water. So given this problem description, your problem is to create the search tree and discuss which search strategy is appropriate for this problem. Question number 2, consider the following graph. Starting from state A, you execute DFS. G is the goal node. You have to show the order in which the nodes are expanded. Assuming that the alphabetically smaller nodes are expanded earlier in case of ties. On the same graph, you also run iterative deepening search. That is your problem 3. With this, we end today's lecture. Thank you.